of the active sites.
So next up, we have Professor Charlie Sykes from Tufts University. He's a professor there at the chemistry department, and he's going to be talking to us about their work with single atom alloys and all the unique properties they have for the ability to break linear scaling relations. And just one note before you start, Charlie, if you could hit the display settings and switch to presenter mode, because we're seeing the opposite on this end over here. So the display settings for your power, yep, there. And yep. It's a little cut off. So if you could try exiting your full screen and entering again.
Any better?
Yeah, if you can just try that, swapping that presenter mode one more time. Yes, perfect.
Okay, you can hear me okay?
Yes.
Great. Well, first, massive thank you to the organizers. It's such a wonderful break to the monotony of sitting home alone to be listening to all these interesting talks. So thanks so much for putting it together. So I'm going to tell you a short story today about what we call single atom alloys and really try to focus on opportunities for breaking these linear scaling relationships. But I'd like to start by dedicating this talk to my late friend and colleague, Maria Flitzani-Stephanopoulos, who passed away in October. And this is actually a picture of a lot of us from the last ACS meeting, which was just in August in San Diego. So, as a very brief introduction to the area, heterogeneous catalysis, as you all know, is a very complicated topic, all the way from the large-scale reactor design and optimization, all the way down to the atomic scale structure of the active sites themselves. And that's where chemists like me are really interested in understanding structure-function relationships in terms of the atomic scale structure of the active site and how that affects the chemistry of the reaction. So there's many great heterogeneous catalysts operating as we speak in industry, but there's still room for improvement. In particular, a lot of the elements that are really good catalysts like platinum, palladium, rhodium tend to be fairly scarce in nature and therefore expensive. So there's not enough platinum for everyone to have fuel cells in their cars in the future. Not every reaction in industry is 100% selective to the product, so there can be improvements there. And then deactivation of catalysts over time due to coking, carbon buildup can lead to inefficiencies. And then CO poisoning as well limits conversion in the startup of three-way catalysts. So the talk I'll give today will hint at this new architecture of single atom alloys, being able to address all of these outstanding issues. So this is what a typical heterogeneous catalyst looks like. It's sort of this black dust. They're very complex things because they have all different types of metal particles, atoms, oxides, promoters, alloys, all these different variables. So it's very hard to sit down and rationally design a better catalyst. And that's why we're all on this meeting today, because for years people have thought of ways to understand how heterogeneous catalysts work. The volcano relationships are a very useful way of understanding it in terms of balancing the binding strength of your intermediates or your reaction energy with the activity of the catalyst itself. And as you can see there, platinum and palladium, these expensive elements come towards the top. And they're really underpinned, these relationships, by Brønsted and Polanyi plots, which really show these nice linear correlations on the single metal, pure metals, where you're looking at the reaction energy of each particular reaction step and correlating that with the activation energy. So you see that the stronger you bind, the more exothermic the reaction step, the lower the activation energy and the faster the rate. So that's great in terms of really bringing forward the understanding of how things react on catalyst surfaces. But in the way we're all talking today, you're still stuck with these linear scaling relationships. What you'd want to have is you'd want to have catalytic metals or other with points down here. So lowering your transition state or your activation energy while keeping the weak binding of the intermediates on the surface. You'd really want to be looking for points on the underside of the scaling line. So one very nice example from theory from Manos Mavrakakis's group from over 15 years ago of potential for escaping these linear scaling for the pure metals is for hydrogen dissociation on what are called near surface alloys. And this is where you have a single layer of one metal on top of the bulk of another, or sandwiched between the top layer and the bulk of another metal in this sort of sandwich structure here. And what Manos is plotting here is the line here is for the single 1-1-1 surfaces of the noble metals, where you have a correlation between the binding strength of hydrogen atoms on the surface more strongly bond this way, and a lowering of the transition state energy for activating the molecular hydrogen. And what he's plotted here is for a lot of these near surface alloy combinations, you can dramatically reduce your activation energy for dissociating molecular hydrogen, but also keep the weak binding of the hydrogen atoms on the surface so you can get both things that you want. And that's a very exciting result. It's harder to implement generally because it's hard to make core cell structures, and then even harder sometimes to keep them in this, or particularly this format during reaction, because under reaction conditions these may restructure. This blue element may come to the surface if it binds more strongly to the intermediates. So in my lab we've taken a different approach. Because we work in ultra high vacuum, we have scanning tunneling microscopy. We can examine surfaces with atomic scale resolution. And what we've been doing for the last 12 years is to take a less reactive host metal like a copper 1-1-1 surface you see atomically resolved here, and then put tiny amounts of palladium, for example, more catalytically active elements into it, where basically one copper atom pops out and a palladium atom takes its place. And that's what we term a single atom alloy. It's an alloy at the atomic scale where you have just single atoms of another more reactive element replacing some atoms of the host metal surface. And today I'll try to convince you that these single atom alloys generally can escape these linear scaling relationships. So we start the experiments with our host metal surfaces. Typically we use copper or gold or silver, which are more inert, weaker binding metals that typically exhibit high selectivities but low activities in the reactions they catalyze. And then we look at the periodic table and we look to the left of those elements and we find more reactive dopant atoms we can alloy into the surfaces. So palladium, platinum, nickel, we're now onto rhodium. And what we find in some cases, like palladium gold, platinum copper, palladium silver, nickel gold, is that we get this nice atomic dispersion of just single atoms substituted into the host surface. Other combinations like silver copper don't mix too well at all, where you get mostly separated domains. And then this case of platinum gold, you actually see you've got both single atoms and small clusters. And it's really due to the mixing enthalpy, where the ones that form single atom alloys have a negative mixing enthalpy. So for example, nickel would rather be surrounded by copper than other nickel atoms. So the thermodynamics drives the atomic dispersion of these. Whereas I'll show you later, platinum and gold have pretty much zero mixing enthalpy, which means the formation of single platinum atoms or clusters is equally preferred, and that's why you see a distribution of sites. So if you can do catalysis this way, you can obviously make a big cost saving if you have something like platinum alloyed in copper, because of their vastly different price differences. And like I say, a lot of the experiments I'll show today are working at the 1 or 2% doping levels of the expensive reactive element. So we start with incredibly clean surfaces, and I'll talk today about copper. And it's very important to have a clean surface because you don't want to be looking at the reactivity of minority defects in these surfaces. So we can clean these surfaces in ultra-high vacuum to better than 1 part in 10,000 atoms. And then we basically heat up samples of palladium, for example, that you evaporate small amounts of palladium, the atoms fly through the vacuum, land on the copper surface, and you can see in the STM image after the alloying has been done that around the monatomic step edges you see all this rumpling. But if you zoom in with atomic resolution, and again we've only put 1% palladium into the copper surface, we see some single atoms in the surface and some single atoms underneath the surface. So the ones in the surface layer are slightly brighter here, and the ones underneath are slightly darker here. And depending on the temperature we make the alloy, so just above room temperature, you get palladium imaging like bright spots. Now they're not palladium atoms on the surface because STM is so sensitive to the Z direction that they're only about 10 or 20 picometers higher than the surrounding copper. So this is showing the side view of the surface where the palladium atoms are substituted into the copper surface. And then if we go to a higher alloying temperature at 500 Kelvin, you see mostly dark spots there. And that's because palladium has a higher surface free energy than copper. It has more of a tendency to be surrounded 12 coordinate by its host. So thermodynamically in a vacuum, palladium would rather be underneath the surface or in the bulk, as apparent here. But then what we know from high pressure XPS work, for example, is that if you have a surface like this with a catalytically active element under the surface or in the core, if you run a reaction over the top or flow things like carbon monoxide, those elements will actually be stabilized back at the surface. So the thing to remember is alloys are very dynamic, just above room temperature in terms of how they respond in their surface composition as the reactive atmosphere is changed. The important thing here is that you don't see any long range order. You can stare at these images all day. You'll never see at the low coverage regime any palladium dimers in this copper surface because of that negative mixing enthalpy of palladium and copper. It would rather be surrounded by copper. So again, it's really the thermodynamics that drives the atomic dispersion. Now to talk about the first class of reactions, hydrogenation reactions, because you quite often want to be selective in these reactions, you don't want to run your catalyst too hot in temperature. And in that case, hydrogen activation can be rate limiting. So let's talk about the energetics of hydrogen dissociation on pure copper and pure palladium, and then look at the mix. So on pure copper, hydrogen will not dissociate in a vacuum. You actually need a molecular beam to bring the hydrogen molecules in with higher energy in order for them to dissociate on the surface. But once you do, they'll recombine and desorb with regular second order kinetics. Whereas on palladium, easy to dissociate molecular hydrogen. You can get plenty on there below 100 Kelvin, and again, second order desorption. But if you looked at these two temperature programmed desorptions, you would see that the temperature which the hydrogen comes off the surface is almost the same, and you would naively think the reactivity of these two metals towards hydrogen was almost identical. But what we know from other measurements, beam measurements in theory, is that hydrogen dissociation has this high barrier on copper, but once the hydrogen's dissociated, the hydrogen atoms are bonded weakly to copper. Whereas in palladium, there's almost no dissociation barrier, but then the hydrogen atoms are bonded much stronger to palladium. So the question is, what do you have when you have just single palladium atoms? And just to make a note about the temperature programmed desorption, the reason they both desorb at 300 Kelvin is to basically recombine the hydrogen atoms on the palladium takes this amount of energy, is about 300 Kelvin. And then microscopic reversibility says that on copper, you have to come back over that dissociation barrier to desorb. And again, that energy is about 300 Kelvin equivalent in a desorption experiment. So the question is, what does the energy landscape look like when you have just single palladium atoms? And what we find is that 1% palladium atoms in copper, you can uptake and dissociate hydrogen. And most excitingly, it actually goes on and off the surface 100 Kelvin lower in temperature than on either pure copper or pure palladium, as you see there from the desorption peak. So it turns out the energetics for dissociation and recombination look like this. You have almost no dissociation barrier that we published years ago with one of our hosts, John Kitchen. And then you actually have weak binding to the hydrogen atom, because the hydrogen atom bonds mostly to copper than to palladium because it sits in a threefold site. So it means where it sits has a binding strength more similar to copper than to palladium. And it's also so weakly bound it can spill over onto the copper surface, which I'll show in a minute. So here we're showing for hydrogen dissociation for a palladium copper single atom alloy, we've broken linear scaling because we have both things we want. We have a low activation barrier and we have weak binding of the hydrogen. And the reason for that is that the location of the transition state and the final state for the dissociation are decoupled. So in a simple sense, the transition state is benefiting from the palladium atom's electron density in order to lower that energy, whereas the final state has the hydrogen atoms bonded to 2 copper atoms and 1 palladium. So it has a fairly weak binding strength, which decouples the two and allows you to have low activation and weak binding. And more recently, a group led by Mikhail Stamatakis at University College London has computed Brønsted and Polanyi plots for the pure metals for hydrogen dissociation, as seen here in blue, and then for a lot of single atom alloys seen here in red. And what you can see is that there's no real linear scaling anymore. There's a big cluster of points here. But most excitingly, it lies on the underside of the curve, which means for all these combinations, we should have a faster rate of dissociation of molecular hydrogen while keeping the weak binding of the hydrogen on the surface. Now, if the hydrogen can spill over from the final state here onto the copper surface, the situation gets even better. For example, if that's palladium copper there, if the hydrogen spills over, it'll have binding strength similar to pure copper, which is here. So it'll actually move this point all the way to there. So you'll have even weaker binding to the hydrogen and a low dissociation barrier for the activation of the hydrogen. So we can go look for hydrogen atoms that have spilled over with the 5 Kelvin scanning tunneling microscope. And this is an image showing that this is the region where the single atom alloy is with the palladium atoms above the copper step. And you see the whole surface is now covered in these small brown depressions, which are individual hydrogen atoms on the copper surface, even far away from the area where the system is alloyed. This is all pure copper, as you see here from the standing waves. You have these two-dimensional puddles of not molecular, because that would desorb, atomic hydrogen atoms on the surface. And we can image the dynamics of these, and you can see the fast diffusion of the hydrogen atoms on the copper surface here. And it turns out that's actually mediated by quantum tunneling in the diffusion, through the diffusion barrier. Because if you do the same experiment with deuterium atoms, you can see on the right here, the rate of diffusion of the deuterium atoms on the surface is a lot slower. So I hope here I've convinced you that just by depositing molecular hydrogen on these single atom alloys and then cooling all the way down to 5 Kelvin where we can image the hydrogen atoms, that they have dissociated at the palladium site, but then spilled onto the copper surface where they're weakly bound. And then we can test the reactivity by, this is just a model reaction trying to hydrogenate styrene to make ethyl benzene. And we see that on the single atom alloy surface, we get 100% selectivity to the ethyl benzene. Another example is for a more relevant reaction, hydrogenating acetylene to make ethene. It's 100% selective, whereas if you do the same reaction on a surface that contains a monolayer or two of palladium, as seen here in the STM, you only get 33% selectivity to ethene. You get all this high temperature hydrogen, which means that you've left carbon behind on the surface and decomposed the molecule you've tried to hydrogenate. And this is really a stark example of an ensemble effect, where in the single atom alloy case, you only have single palladium atoms, which are able to dissociate hydrogen, but they're not able to decompose your reactant because palladium will overbind acetylene and basically break it down to carbon. And that's why you see this hydrogen released here. So in the single atom alloy case, you can break the bond you care about, the H2 molecule bond, but you don't dissociate the molecule itself, which leads to coking and deactivation. So is this effect general? I've told you that story about palladium copper. So we moved to platinum because platinum's ubiquitous in many different important chemical reactions. And we chose this reaction here, which is the selective hydrogenation of butadiene to butene. This is important for the polymer industry, which tries to take this impurity out of propane feedstocks for polymerization. So you really want to make butene, but not butane. And what we see on a 3% single atom alloy platinum copper surface is we see 100% selectivity to butene, no butane, and no high temperature hydrogen. So we're not decomposing the molecule. So that looks very promising. And then what we can do is show turnover in UHV, where we basically do the same experiments 18 times in one day on the same surface, and we basically get the same high conversion to the product. We see the same uptake of hydrogen, and we titrate the platinum sites as well. So you can see that multiple cycles on this surface do not lead to poisoning as it would be with a platinum or palladium surface. And now, because we have the scanning tunneling microscope, we can ask the question, where does each reaction step occur? So this is STM on the left here, which is basically shown in this cartoon here. So this is an experiment in which we have platinum atoms on a copper surface. We've exposed it to hydrogen. The hydrogen is dissociated, spilled over. Hydrogen's the red dots here. And then we've absorbed a little bit of CO, 1 or 2%, to just selectively bind to the platinum sites because it binds to copper so weakly. So what you see here is the black circles here are the CO molecules absorbed on the platinum atom sites. And then all the streakiness around them is that fast diffusion of the hydrogen through quantum tunneling. So basically, I'm just showing you this model should be correct. Then we image at slightly higher bias, which basically sweeps the hydrogen away from the area. And now you just see dark spots there, which is every platinum atom as the surface is capped by CO. And then we pulse each CO molecule at 5 volts, tunnel into the LUMO, desorb the molecule, and then you can see the position of every dark spot here. Underneath it, there's a little bright spot, and that's the platinum atom in the copper surface. So this basically just tells you that the hydrogen spilled over onto the copper, and that we can selectively titrate the platinum sites with CO. So in the next experiment, what we did is we ran the reaction without CO, and then we put 1% CO on the surface after the hydrogen had spilled over, and we ran the hydrogenation reaction through a temperature programmed desorption. And what we see in both cases is the same conversion of butadiene to butene, whether the CO is on the platinum or not. So what that means is that the hydrogenation step of butadiene to butene happens on the copper, whereas we know that the dissociation of molecular hydrogen happens on the platinum because we put the CO there first. We don't dissociate the hydrogen. So this is showing in the model catalyst in UHV that it happens via a bifunctional mechanism, which is a very hard thing to prove in a working catalyst. And then we can address the ensemble effect again. This is an example. We've now gone up to 30% platinum on the surface. It forms these one-dimensional chains of platinum atoms. And what you can see straight away is that just by having a one-dimensional chain of platinum atoms, not even a nanocluster or anything, just a 1D chain, you've switched off your selective conversion of butadiene to butene. And you have all this liberation of high temperature hydrogen, which means you're breaking down your molecule on the surface, forming carbon. So again, the single atom alloy is an extreme example of the ensemble effect, where the single atoms will not decompose your reactants, whereas one-dimensional chains will. So everything I've told you so far are experiments in ultra-high vacuum. I've shown you can have great atom efficiency in terms of making your catalyst. You can break linear scaling. I've shown you for hydrogen dissociation. You have a bifunctional mechanism of hydrogenation that can be very selective. So the question is, does any of this matter? Does it translate to relevant conditions in a reactor setup? And that's where my late colleague Maria Stephanopoulos in her group contributed massively to this project in demonstrating the first single atom alloy nanoparticle catalysts. This is a TEM image of a platinum copper catalyst. This is XAFS data showing the dispersion of the platinum, that there's no platinum-platinum bonds detectable. And the strongest evidence for it being a single atom alloy catalyst is infrared spectra of CO, where on the 1% platinum copper single atom alloy catalyst, we see only a bond. We see only a peak in the infrared spectra for COA top platinum. We don't see any bridge bound CO. So at the surface, what we have is single platinum atoms in the copper surface. And then for running a reaction, we tried again the thing we had done in ultra high vacuum, butadiene hydrogenation. What you see is on a pure copper nanoparticle catalyst, the light off doesn't happen until about 100 Celsius, whereas just putting 1% platinum atoms into that copper nanoparticle drops that light off temperature by 50 Celsius. And most importantly, you keep the high selectivity towards the butane that you want because of the copper doing most of the chemistry. And this is just showing for a day on stream in an industrial gas flow where you have a lot of propane and you're trying to take out the butadiene. You see high selectivity to butane and you touch less than 1% of the propane in the feedstock. So this looks like a really promising catalytic system. Another thing we noticed during these experiments is we noticed the carbon monoxide, a common poison, binds more weakly to single atoms of platinum than to extended platinum, as you see here. So we went back to Maria's group and they tested this for the selective hydrogenation of acetylene to ethene in a flow reactor. And what they did is they compared to regular platinum nanoparticle catalysts. And when you add 200 ppm of CO, you see you lose 90% of the reactivity of the regular platinum nanoparticle catalyst, whereas you only lose half the activity of the 1% platinum catalyst because of that weaker binding of CO, that the reaction can proceed because more of the sites are not poisoned by CO as compared to platinum, which binds CO much more strongly. So that was hydrogenations. What about dehydrogenations? There's a big interest with shale gas, CH activation, and also making alkenes to go into polymers. So CH activation is rate limiting typically, and coking is a big problem because you need to use reactive elements for this. So what I'm showing here is experiments we're doing with methyl groups that we add to the surface via dissociating methyl iodide. And on a copper surface, you have to heat it up to about 450 Kelvin to break CH bonds in the methyl groups to basically make hydrogen, CH2, and then make ethene and methane. So this is basically a reporter of the temperature which CH activation happens on copper. Then we put just 1% platinum atoms into the copper surface. We do the same reaction, and what we find is CH is activated 100 Kelvin lower in temperature when you have single platinum atoms in the copper surface than on pure copper. And we can go in with the STM and we can image the reactants here, the intermediates here, where the bright spots are iodine atoms, the darker spots are methyl groups. And you can see on copper, you have to go all the way up to 450 Kelvin to activate CH and methyl, and then couple to ethene, propene, make methane, and only leave behind iodine. So it's a clean reaction. But you can see clearly here that when you have just 1% platinum atoms in the surface, your reaction's finished by 350 Kelvin. All you've got left over is the iodine atoms that came from the methyl iodide. So that's demonstrating that you can do very clean chemistry where methyl goes to ethene, propene, and methane just by adding 1% platinum to the surface. And you see we start with a half a monolayer coverage of reactants, and just 1% platinum does the job because these intermediates will diffuse around the surface, find a platinum atom, CH activate, CC couple, and give us our coupled products. So again, go in to test that to see if it works under industrial conditions. So this is now taking butane, sort of shale gas analog, and running it over the 1% platinum copper single atom alloy catalyst and gas flow in the reactor. And you can see at 400 Celsius, that catalyst is stable on stream for 2 days in converting butane to butene and hydrogen. And we don't observe any coking. whereas the platinum catalyst is very active, but even after the first cycle, half an hour later, you've coked most of the sites and the activity dies off and you've covered up most of the sites. So this is a very interesting direction for CH activation, where the single platinum atom will lower that barrier significantly. But because the surface is mostly copper, you can keep your high selectivity, you don't coke, and you can also do CC coupling. And this is really nicely explained by Mikhail's group, where they plot out the energetics going from methane, methyl, CH2, CH, carbon. On platinum, that is exothermic to form carbon on platinum. So that's why platinum catalysts will coke. Whereas these single atom alloys, the red line here, will reduce the CH activation barriers, but it's exothermic, it's endothermic to coke. So you can basically go over the first step or two and then no further, which gives you the selectivity. So in the last 5 minutes of the talk, where are we going next with this? So you can imagine we've got a lot of different combinations that we could think about in this geometry. But the first thing we need to know is which combinations will likely form single atom alloy. And this is where theory work is incredibly useful right now, because the active site is so simple, you can model it very accurately on a 3x3 slab. And this is results from Mikhail's group showing that any alloys that lie above the line, this is the aggregation or the mixed enthalpy, any alloy combinations that lie above the line should be atomically dispersed, and any ones that lie beneath the line should segregate into, for example, iridium and silver areas. And one thing we use to benchmark the DFT calculations is the binding energy of CO. This is the gray bars here are the results of DFT parameterized KMC simulations for the desorption of CO. And then the diamonds here are the ones we've measured experimentally so far. So we get very good agreement for the binding of CO to these different single atom alloys as predicted with theory. Now, this is probably one of the most exciting graphs I've seen, but it doesn't quite look like it. But what this is this is both the reaction energies for a bunch of different elementary reaction steps along with their activation energies. So this is for hydrogen dissociation, CH activation, NH activation, OH activation, and CO2 reduction. So now we know for all these different combinations of metals in the single atom alloy geometry, what the activation barrier and reaction energies it is for these steps. So now if we want to design a catalyst that, for example, activates CH bonds but not NH bonds, we can look through these tables to see for a low activation energy for CH, high for NH, and then choose that and test it. And then relevant to this meeting, a lot of these combinations will give you different scaling relationships or completely break the scaling relationship. So again, this is calculated activation energy on the y-axis, reaction energy on the x-axis for hydrogen dissociation, CH activation, NH activation, and so on. The blue lines are the linear scaling for the pure metals. The red points are for the single atom alloys. So you see in a lot of cases, you're actually lying underneath the blue line, which is good because you have lower activation energies for weak binding of intermediates. I'd encourage you to take a look at this perspective article in JPC Letters, which I borrowed the title for this presentation, for a discussion of all these different properties predicted from theory. Now, as the last 2 minutes, you know, why are these things so different? Why are we getting all these different properties from this atomic geometry? Now, it's not quite what you would sort of intuitively think, because one of the things we found from the DFT calculation is if you use beta charges and just look at the charge on, for example, a single platinum atom in copper, it predicts it has more than half an electron charge negative on the platinum and the copper versus nickel and gold, which has a deficiency of 0.3 of an electron. And this is basically because you're putting unsimilar elements together which have different ionization, electron affinities, and so on, and you do get charge transfer between them. So even though you'd think of this typically as it's an alloy, the electrons are smeared everywhere, it's neutral. The old view of alloys is that you put elements in, you subtly shift the D band to get properties you want. this is quite different because you don't have this mean field view of the surface. It's actually quite localized where you have charges on these atoms. And then most recently, this is something John Kitchen calculated years ago, is that you have these free atom-like states of the single atom alloy. So this is a recent paper from Robert Schlogel's group looking at copper atoms in a silver host. And what you can see from the synchrotron XPS is that this is the D band of the silver host. Whereas you put a single copper atom in, you have a localized copper state. There's very little hybridization of the copper atom with the silver host, which means the electronic structure of this copper atom looks much more like a copper atom in a vacuum than it does a copper in a copper metal. So it's because of the lack of hybridization between a lot of these combinations, you get these localized D states, and that's where a lot of the reaction can be centered, and that sort of breaks you away from typical the D-band model and so on. And I'll point you towards a fairly recent paper by John's group that discusses a lot of these computed electronic structures and the effect on reaction barriers. So I'll leave the conclusions up when I finish, but just to thank the people that did the work. Again, this has been about 12 years of experimental work from my group here, from Maria Stephanopoulos' group, from Mikhail's group in London. And I'd really like to thank the Department of Energy for years through a CPIMS grant to really do the fundamental surface science to develop these things, and then a joint grant through the Catalysis program I shared with Maria Stephanopoulos to realize a lot of these systems in more industrially relevant conditions. And thanks for your attention on this call.
All right, thank you very much, Charlie, for an excellent talk. We've got quite a few questions. We'll try to get through a couple of them before our break, and then as always, we'll be posting these to a Google Doc. So a few of the questions have been along the lines of the agglomeration of these single atom alloys or their stability, and so if you could comment on what you've seen with that.
Yeah, to reiterate, a lot of these combinations I'm showing here, thermodynamics drives the atomic dispersion, because if your aggregation energy is positive, your tendency is to isolate palladium atoms in the gold surface is more stable than a cluster of palladium atoms. So for a lot of these metal combinations, it's just the mixing thermodynamics that gives you the atomic dispersion, where a lot of these combinations work, but not, for example, iridium silver would be a bad choice. Now, in terms of stability, the thermodynamics keeps it well isolated, but then in terms of a reaction, you're going to have reactants on the surface, and that's what stabilizes the atoms in the surface, whereas if you flow hydrogen or helium, they may disappear into the bulk. So it's really the reactions intermediates on the surface are stabilizing those single atoms in the surface layer and allowing the catalysis to proceed.
Another related question, I'm trying to merge a couple of the ones here. There's been some interest about how much loading can you have of these single atom alloys as a maximum, and under catalytic conditions, how much of those would you expect to be subsurface?
Good question, and it's a tough question because of what I just mentioned, is that depending on the partial pressures in the gas phase over the catalyst, that will dictate under steady state what the population of atoms in the surface. So every different reaction will have a different percentage population of those single atoms in the surface versus the bulk. But you can play tricks like you play in regular catalysis. You can make small particles that you have more surface area per bulk. That's a way to up the active site number. But I would say it depends on the reaction you're trying to run. In terms of stability, we've seen other people in the field run these catalysts up to over 500 Celsius, and they're still atomically dispersed. The only stability issue we have right now is just sintering of the host metal itself. For example, copper and silver and gold are very liable to sintering. So the activity shuts down, not when the single atoms disappear, they're always there due to thermodynamics, it's when the particle sinters and loses surface area. So that's why we're looking into things like atomic layer deposition to stabilize the host metal itself and then keep this chemistry even hotter in temperature.
All right, well, thank you again, Charlie, for an excellent talk. We'll be getting the rest of these questions to you, and then we'll post them on the Google Doc for everybody to see the answers to them eventually. Well, thank you.